Okay, so good morning, everyone. Happy New Year, and welcome back from the holiday. So today we are going to enter to the main content of this course about supervised machine learning. And so we will talk about three main content this course in this class. So there are two important concepts in machine learning, which are gradient descent and regularization. And we are also going to talk about a simple machine learning method called linear regression. Yeah, and actually these days, gradient descent and regularization, like it's all about mathematics, but advanced machine learning method, they already put these things in the library. So when you're doing coding, actually, you don't really know the underlying mathematics. But maybe in your job interview, if you are going to do something related to machine learning, they will ask about these kind of things. Okay, so let's start. And so we've talked about there are several kinds of machine learning tasks, like classification and prediction. So today we are mainly going to talk about prediction. And so prediction is mainly to predict the value. So it's like to predict the stock market, like the price of each stock, like in the future, and also like to predict the temperature or weather in the future. Yeah, there are some examples about prediction, but it's not quite important. Let's directly go to the first machine learning method, linear regression. So when we talk about prediction, actually, it also means regression. So when we say predict the value, it means regression. And when we are talking about predicting a label, it means classification. So in regression, the most basic or the simplest method is the linear regression. And so linear regression is like this. So it will give you some instance, let's say in a two-dimensional axis. So you can see there are some instance like the points here. Those are some instance with some x value and the corresponding y value. Okay, like this point. So we have quite a lot of instance here. So we have quite a lot of instance here. So we have its x value, and then we want to predict the y value. So it means we want to learn a function f to predict the y value for some new x value. So for example, if I tell you that there's a new point whose x value is 1.5, and then you need to find out what should the y value will be. So it's kind of predicting. And then there are many possible functions for this f that map x to y. But which one should we choose? So actually, we don't have any idea about which function we should choose. But we can make some assumption about this. So let's see. What is the eraser? Okay. Let's see. Let's have a simple example here. Let's see this one. This is a linear function, right? So this θ1 means the slope. And the θ0 means the intercept. So slope means the tangent. Let's say you have a function y equal to θ1 x plus θ0, right? So this part means θ0, the intercept. And the tangent value of this angle means the slope. So this is some basic function of the mass, a basic concept of mass. Okay. And then okay. And then let's see, let's make an assumption. So as I said, we don't know what the function will be. So it can be a linear function as we've just introduced, like this, right? And it also can be some other functions. For example, it could be like this, or some more complicated functions. So this may be some functions like y equal to ax plus squared, ax squared plus b, something like this. And this is a linear function. And so when we are doing modeling, we need to first decide what the function will be. And we might try different functions to train the model and then to see the performance to decide what the function should be. And when we are talking about linear regression here, it doesn't mean the function should be linear function, okay? So this is a very important concept. Linear regression doesn't mean the function of the model should be linear like this. So linear function means ax plus b, y equal to ax plus b. This is like linear function, okay? And if you are talking about this function, then it's not linear function. But in linear regression, the model can either be this function or this function, or even with more complicated function like polynomial. And so yeah, the point here is that the function doesn't need to be a linear function. When we talk about linear here, it means the parameters. Sorry. It means the parameters here are linear. Okay. Then there are some key questions in linear regression. So the first one is like how we parametrize the model. So how we define the parameters of the model, it means. And like what loss functions do we use to judge the model? So when we are training the function, when we are training the model, we need to deduce the loss of the model. So this part we'll talk about later. And so we will have a loss function and we need to minimize the loss. And then how do we, according to the loss function, how do we optimize the model to the unseen test data? It is also called like generalization. We've already talked about this concept in the previous lectures, generalization. So it's like to have a good performance in unseen data sets. Okay. Then let's have an example here. Let's say there's a mouse. There are several mice. Yeah, there are several mice. And we know the weight of the mice. And we want to predict the size, or we say the length of each mouse. So now we already have some instance or some samples of the mice we have. Okay, so let's see, these are all the data for the mice. And so we can see for each data, it has it's corresponding to a single weight and a single size. So this represents the relationship between the weight and the size of a mouse. Then we want to find a line that fit these data points. So intuitively, we may think that the function should be like this, right? So a very simple function like this, a line to represent for the relationship between the weight and the size of a mouse. But how we find this line? like how we find the best line that can fit all the data. So firstly, let's see, we have a random line here. We draw a random line here through the data, and then we measure the distance from the line to the data. And then we square each distance and then add them up. So for each data set here, we measure the distance. The distance means the points from the line, the distance from the point to the line. And then we calculate all the distance for each data point and then sum them up. Okay, and then yeah, so because sometimes the value would be positive, sometimes would be negative. That's why we need to square the distance. Because if you use these data points, like for example, it is 1, 2, 3, 3.5 minus like this data point, which is 1, then it is 2.5. However, if you use this 3.5 to minus this maybe 4, 5, 6, this 6, value 6 here, then it will be minus 2.5. So that's why we need to do a square operation to keep all the values positive. Okay, and then after we calculate the squared value of the distance, then we just add them up to calculate the whole, the total distance. Okay, and this is also called the SSE. This is called sum squared error. Okay, so it means the squared error, the summation of the squared error. We call it at SSE. And then, so we can see in this figure or in this slide, with this line we draw here, then it will have a very big SSE because all the data points are far away from the line. However, then we rotate the line a bit. We change the slope and the intercept of this function. And then we measure the residues again. So residues also means the loss, okay? So it means like the difference between the data and the line. Always see the distance. So here the residue is just the SSE that we mentioned here, SSE. So this means SSE here, okay? And so we can see that the residue, the SSE value, is getting smaller when we rotate the line. And then we rotate a bit more. And then we calculate the squared residue again. And we can see this residue is much smaller. So we can actually have a plot of all these value of SSE. So this is a plot. This is a plot of SSE, okay? So this is a plot of SSE, sum squared error. So here we have different kind of rotation of this line. So this is initial line that we draw at the first slide. So we have a value of the squared residue here. And then in this way, we draw all the residues, squared residue here for each different rotation of the line, okay? And then we can find out that this line, in this slope and intercept, it has the lowest sum of residue. Then it means this line fits the data best in all these lines. And this is also called the rotation or the function with the least squares. So if you already learned about linear algebra, then you will know there's a method called least squares to define the interval and the slope of a linear function to fit a data set. But in machine learning, yes, actually in machine learning, we also use this for linear regression. But today we are going to talk about some other method like gradient descent to solve this linear problem. Okay, so like we can see this least square rotation can feed the data best. And then finally, we got intercept and the slope for this function. And this is the final function that feeds all the data the best. And then next time when there's a new data come, for example, we have a new mouse. And the mouse has a weight of 2. Then we can predict probably the size of the mouse will also be around 2. Yeah, so that's how we do prediction for the new data. Okay, so this procedure is called fitting the data. So it means we want to find parameters that reduce the misfit or the loss or the residues. So there are a lot of terminologies, but they have the same meaning. And yeah, so we want to reduce the loss between the model and the observed data. And so there's, in the previous example, the loss function we use is the sum squared error, SSE. Okay, and then it's very simple. So it's like we have a model f theta, right? And then we just put the value of x in our model. Let's see, we take this point as an example. And then we have x value, like say 0, right? So we put this x into the function f theta. So this f theta is the model that we train. Okay, f theta means the model. Okay. So actually in machine learning, model and function have the similar meaning, but model sounds more advanced. That's why I usually call it model, but actually it's just a function. But sometimes the function is very complicated. That's why we call it model. And then we put this data x into the function or the model. We have a value, we have predict value. So this is f theta 0. So this is the predict value. And then what is y here? Y means the actual. Oh, sorry. Yeah, I made a mistake. Yeah, so I draw a wrong line. So yeah, this is the predict value, okay? This is predict value. So this is f theta 0. This is the value we predicted. And then y here means the actual value. So this data point, this is the real data point. So this is the actual value. So this is let's see, y0. Okay. And then we just calculate the difference between this y0 and this f theta 0. So this is like this procedure. And then we square the residue. Here we square the residue and then sum all the data points up. So we have in total, for example, here it said m. You can see here, right? M. M means there are in total M data points. And we do summation from 1 to n. So like the first data point, we do all the same procedure as this data point and sum up all the squared residue together. So this is the SSE. And MSE is just the mean value of SSE. So we put another term here. 1 divided by m. So this is to calculate, because in total we have m instances. And then we calculate the average of the squared error. And this is called MSE. So there are two kinds of loss function. Okay, so this concept is important, loss function. In the following classes or labs, all the models will have a loss function, okay? And then your job is to just like to deduce the loss according to the loss function. And actually, when we are doing machine learning, so for each kind of model, we can define loss function by ourselves. But yet, because it's already very developed, so there are already a lot of loss functions that you can choose, and there are some good choices for each model. So basically, you don't need to design your loss function unless if you are doing like more advanced things, maybe in your master or PhD, or we can just use the existing loss functions. Yeah. So our target is to minimizing the cost function. Okay. So sometimes the loss function is also called the cost function. So minimizing the cost function and find the optimal set of weights that can be optimal set of weights. So in this case, let's see, we have a linear function y equal to theta 1 x plus theta 0. So we only have two parameters here. So when we say optimal, we find the optimal set. It means the optimal value of these two parameters. Sometimes we have more parameters. So it means a set of weights. So the parameters in a model is also called weight sometimes. Yeah. Okay. So to minimizing the loss function, okay, they have the same meaning, loss function and cost function. So it is to minimizing this loss function or cost function, it's also called optimization. Optimization, it's also called. And to solve an optimization problem, it can be hard. Okay, so there are different kinds of optimization approaches, and we need to first choose like the model, and then the error function, the loss function. Okay. Yeah, so just summarize. Error function, loss function, and cost function. Function. They have the same meaning, okay? No matter it is error function, loss function, cost function, they are the same. Usually we just call it loss function. And so, yeah, so you can say that when you are doing a machine learning task, you need to choose model, loss function, and then also optimization approaches. So there are a lot of choices for you to do. And the good thing is that as we've investigated, I mean, people have investigated machine learning for already many years. So they already find like gradient descent. The gradient method could be the optimal optimization approach in the machine learning tasks. That's why all our machine learning tasks in this class will be based on gradient descent. And actually these things you don't need to know about, okay? It's like old school style. And so then let's have a summary of how linear regression works. So it works by fitting data to a linear model in the following steps. Okay, so we initialize the model by assigning a random coefficient to the function. That means random parameters. Like this set of parameters, theta 0, theta 1 to theta n. So we firstly just initialize the model with some random parameter, like we do in the previous example. We just draw a random line on the data. And here, so it said theta is the coefficient vector. Yep, so if you write this in a vector style, it can be this parameter can be recognized as a set of a vector. So like theta 0, theta 1, theta 2, blah, 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 theta n. So it's a vector. This is a set of parameters. If you write in the vector style, it will be like this. And so the first one, the first term here, x0 is taken as 1 usually. So we don't need to talk about x0. So this is the intercept of the function. And previously, we only have one variable x. But in this example, we have a lot of different variables, x1 to xn. So it is like a multivariable. And that's why it has multiple parameters for different variables. And but no matter how, there will be an intercept here, a constant value here. And okay, so like this function can also represent like a hyperplane. So hyperplane here means just like a multi-dimensional plane, okay? So we know like a line. Usually when we are talking about a plane, it means a two-dimensional plane, right? Like this is a plane and this is a line. So in the concept of hyperplane, it's just summarize all these kind of planes into the same terminology of hyperplane. So when the dimension of a hyperplane is 1, that means a line. Then if it is the dimension is 2, it means a normal plane, a general plane, and it also have dimension of 3, 4 or more, much more. So we are not able to present in the graphical way. That's why we say it's a hyperplane. And yeah, and then we have some input sample with labeled data, like the samples we have in the mouse example. So we have several mouses. Sorry, we have several mice. And then each mouse have their weight and size. So this is like samples. So in this case, the weight is the input and the size is the target or the label. And then we just copy the loss of the predict output from the target of the model, and then try to minimize the output error, which is SSE or MSE that we've introduced by using gradient descent. So this we will talk about later. Yeah, and then we stop this training process until convergency on acceptable error. Yeah, and that's the main idea of how linear regression works. Okay, then let's talk about gradient descent. Okay, so this is the optimization. Optimization. Sorry, my handwriting is not good. Yeah, all right. Hope you can see. And optimization method, okay? And gradient descent, there are two parameters. Actually, there are only one parameter, I think. Yeah, linear rate. And we do gradient descent on the cost function or loss function. Loss function. So we will have a learning rate. Just keep it in mind, and we will talk about it later. And so let's see. Yeah, the main idea of the gradient descent is like this. So we have a, let's say this is a loss function. And then we calculate the gradient or the slope of the point here. This is the initial weight. This is a random value. So we just randomly pick a value here. And then we calculate the gradient or the slope. Okay. And then we just decrease the gradient. So we take some steps here to this point because we want to reach the minimum point of this function. This is the loss function. And in the previous class, we've already talked about like how do we calculate the minimum point of a function. We use the derivative, right? But when the function is very complicated, we are not able to solve these functions and calculate its derivatives. That's why we need to use gradient descent. So what it is doing, so we want to reach this point here, and then gradient descent doing is like every time take some steps and then calculate the loss. And then according to the new gradient, it take another step, and ultimately it will reach the point here, but not exactly the point here, maybe. Depends on the complex of the task. So it may be reach some point near here. So gradient descent sometimes cannot find the optimal point of a loss function at some point close to the optimal point. Okay, so let's take some example here. So still we are predicting height. Let's see, we are predicting height of a person. Okay, so now we have 3 points for 3 data points of people. Each data point includes the weight of the person and the height of the person. And then we want to predict the person's height according to his weight. So firstly, we choose a function. Let's say to be simple, we choose a linear function. So it will have an intercept and a slope. Okay, so this, and then this weight, which is just like the variable x. So this is actually the theta 0 plus theta 1 x. Okay, so this is the function of the model we choose here. And when we're doing gradient descent, actually we are optimizing the both parameters. But let's, just for illustration, let's take this parameter intercept as an example. Okay, so let's start by using the gradient gradient descent to find the intercept, the optimal intercept in this case. And so, as you've maybe already learned, that you've got a method called least squares in your linear algebra class. And by this method, you can actually directly solve the optimization problem of linear regression. That you can use an equation to calculate directly the intercept, the optimal intercept and the slope for a linear regression problem. And then we use this method, we calculate the slope is 0.64. So we use this 0.64 as an example here, okay? So now we are going to optimize the intercept, the θ1 here. And we assume that we already know the value of θ0 here. And we assume that we already know the value of θ1. Okay, so then we use gradient descent to solve, to find out the optimal value of intercept. Intercept means here, okay? This is intercept. Okay, and yeah, just to revise again, slope means this angle, okay? This is the slope. Yeah, so we are going to use the gradient descent to find the optimal value of the intercept. So this intercept can change like this or like this. So like, because the data here is very simple, we know that the intercept here is better than here, right? Okay. So the first thing we do here is also initialization. So if you still remember that several slides before, initialization means to pick a random value of the intercept, okay? And let's say we use 0 here to start. And then if we put the intercept as 0, then it will be going through the origin here. And in this example, we will evaluate how well the line feed the data with the SS is sum of the squared residue, okay? This is also means SSE, okay, the same concept, sum of squared error. And so it's like just like calculate the distance, square it, and then sum up. So this is sum of squared residues or sum of squared error. And okay, so let's say we have some data point here. The first data point is a person with a height of 1.4 and width of 0.5. Okay, so it looks abnormal. The data looks abnormal, but this should be some normalized data. Okay, so it doesn't mean like the person really have a height of 1.4 and width of 0.5. And okay, then we use this function that we choose at the beginning to predict the height. Okay, so the predict value is here, the cross here. This is the predict value. And because our function is fx equal to θ0 plus θ1x, and theta we've set to 0.64 and θ0 we've set to 0. So this is the predict height of it. So we will have a value of 0.32. Okay, so this is the predict height here. Predict height here, 0.32. Okay. Then we calculate the residue difference between the observed height and the predicted height. Observed height here means the truth, okay, the real truth of the data. So when we have an instance here, we also call this sometimes an observation. And so the observed height here is 1.4, right? And then the predict height here is 0.32. So we just calculate the residue. And then we got 1.1. And then we square it. Okay, we square it. It's the squared of residues. And then in the same way, we have another data point of 2.3 and 1.9. And again, we calculate the residue. It will be 0.4 And then for the last points, we calculate residue, which is 1.3. So we squared all these residues and then calculate the summation, which is 3.1. And then here is the loss function, okay? So please pay attention here, okay? So this part here is the function of the model. And to find out the parameter of the model, we need to optimize the loss function. And when we are doing optimization, the optimization is based on the loss function. So the loss function will be like this, right? So when you are moving, let's go back. So the first time we use the initial value of theta 1 equal to 0, means here, this point. This theta 1 or theta 0, sorry. Theta 0 equal to 0. So theta 0 means the intercept. And when it is 0, we calculate the value of the residue of 3.1. And then we just increase the intercept. And then we can get several points here. So let's see, we increase the intercept from here to here. And then we have a new data point here. And then for this line, this new intercept, we have a new data here. So this is the plotting results of all the sum of squared residues. And finally, we will have a curve like this. Like this. So this is called the loss function, okay? And then we want to find the minimal point here. Yeah. So of all the points here we calculate for the graph, we find out the one has the lowest sum of squared residues. But the problem is like, we are not able to decide if this one is the optimal point. Maybe it is there's another point here. It's even smaller than this point. So a slow and painful method for finding the minimal sum of square residue is to plug a lot of data in this example for all the intercept. So the more data points, the more intercept we try, we'll have more data points on the loss function. And then we will have more accurate optimal intercept. But this method is very slow and painful. So what gradient descent doing is like, it only does a few calculations far from the optimal solution. And then it increased the number of calculations closer to the optimal values. Or in other words, gradient descent identify the optimal value by taking big steps when it is far away from the optimal point. So this is like a step. So when it is far away from the optimal point, it takes bigger steps. And when it is close to the optimal point, it takes smaller or baby steps. So let's go back to using gradient descent to find the optimal value for the intercept. And we again use the random value of 0. With the intercept of 0, here we start with 8. And we're still using a slope of 0.64. This is initialized value, okay? So we still use this function, fx equal to 0 plus 0.4364 x. Okay, so again, we calculate the residue like this. So we have the first data point whose x value is 0.5. And then we just put the 0.5 in the weight. Okay, this is the x. So we have a sum of residues squared of this function. Right? So this is this 1.4. Let's go back. This 1.4 here is the actual value of this, the real value of this data point, 1.4. And then we put this 0.5 here. This is the point here. This is the calculated value. And then this is the calculated value. And this is the function x. We just calculate the distance from 1.4 and this calculated value and square it to calculate the sum of squared residues. Okay, so the first point is 1.4 here, and the x is 0.5. So this is the first point. And then we calculate the second data points. So it is 1.9. Okay, so this is 1.9. And yeah, the weight, okay, here is this is 2.3. So this new point 1.9, 2.3. Okay, and again we put in this function. This is the function the assumption of the function we made. And then we calculate the value of this function by replacing the weight by 2.3. And then in the same way, we calculate the last person's data. And it is as 2.9. This data point is 2.9 to 3.2. Okay. Then, if we want to plot the loss function again, we just need to put all the intercept values inside this function. This is loss function. This is the loss function in respect of intercept. So the variable here is the intercept. And in the previous function, the model function, the variables are the weight. Okay, so that's why we have two functions. This is a loss function. Loss function, the variable should be the parameter. Here is the theta 0 intercept. Theta 0. Okay. And then we plug all the some intercept value inside this function. We got a plot, right? So we will have, so if we just draw the function of this SSE or sum of squared residues, we will have a function like this. Yeah. And then we take the derivatives of this function and then determine the slope at any value for the intercept. Okay. So let's see, we take a data point here. We just calculate the derivative of this function. So this is this red line here is the derivative of the function. Okay, and if you still remember that the content we've talked about last lecture, to find out the minimum point here, the derivative should be equal to 0. Okay. Okay, then we just calculate the derivative. Or we see the partial derivative. Actually, there's only one variable here, so actually it's just the derivative. Okay. Then here is how we calculate the derivative. We just put all the the derivative of the sum of squared error equal to the summation of the derivatives of all these terms, all the three terms here. So we just put them all together. So we calculate the derivative of each term here in this sum of squared residues to calculate the derivative of the sum of squared residues. Okay, and then we start by setting the intercept to a random value. Okay, let's see, we also start from 0 to calculate the intercept. We set it to 0 at the beginning. It is called initialization. It's a random number. Okay, but for example, here we put it as 0 in the beginning. And then we calculate the derivative when it is 0. And we can see that the derivative when the intercept is 0 is minus 5.7. Sorry, yeah, minus 5.7. Okay, the slope of the curve is minus 5.7. And the slope is also called gradient. Gradient. Okay. So yeah, just to mention again here that when we are closer to the optimal point, here the slope will decrease. So the slope will decrease. It means the gradient is decreasing. That's why this method is called gradient descent. Descent means decline. Okay. It also means decrease. So that's why it is called gradient descent. We just want to decrease the value of the slope. Wait, sorry, I'm doing it wrong direction. Yeah, here. Okay, and then, yeah, so this here is just an example that when we are getting closer to the optimal value of the intercept, the slope of the curve get close to 0, or the gradient get close to 0. That's why then we take smaller steps to estimate the optimal value. And when the slope is far away from 0, we should take bigger steps. These things we've already talked about. Okay, but if we take a super huge step, let's say the first step is 0. And then the second step goes here. Then the loss will even increase, right? So this is the step. And if we put a very huge step here, the loss will even increase. I mean, or the slope or the gradient increase. But we want the gradient decrease. That's why what I mean here is that the size of the step should be related to the slope. And the size of step, I mean, the gradient descent method is very sensitive to the step. So the main problem in gradient descent is how to decide the step. But there's a relationship that when the gradient is bigger, we use bigger steps. And when the gradient is smaller, which means it is closer to the optimal point, we use smaller steps. So we can see from this phenomenon that the step of the gradient descent should be proportional to the gradient in each step. Okay, and then let's see, we can have example here. So let's see at the beginning, we have initialization of the intercept of 0. And then we calculate the gradient descent of 0 minus 5.7. Okay, it means then we want to decide the step size. So what we do here is just we put a factor here, a small factor here to decrease the step size. As you can see, the total interval of the x-axis is only 2. And if we put 5.7 here, it is already far away from the, maybe very far away from this function, and it will have a very big loss or gradient. So this step, of course, it is not appropriate. That's why we put a factor here. It is called the learning rate that I've mentioned in the previous slides. This is called learning rate. Okay, so let's just set the learning rate as 0.1 to decrease the step size. And then what gradient descent do is to create a new intercept according to the old intercept and the step size. Okay, and the step size here is equal to the old intercept, the old gradient. Sorry, the gradient in the old intercept multiplied by a small factor. Here is 0.57 negative. Okay. So then we do this calculation. We find that the new intercept should be 0.57. So we take a step of 0.57 and reach to this data point. So this is the original data point. This is the data point after the first step. So we calculate the new intercept of 0.57. So it goes to the step of 0.57. And then to take another new step, we need to calculate the gradient again on this data point. So we can see previously when we calculate the gradient, we are calculating the gradient on this data point. And now, as we've got a new intercept, we are going to calculate the gradient on this intercept. So yeah, so we will calculate the gradient in the same way, or the derivative or the slope, doesn't matter. They have the same meaning. And then we can see this gradient is minus 2.3, okay? And again, we calculate the step size by the gradient or the slope. Here, with a certain learning rate we've defined, which is 0.1, okay? Then the step size we calculate will be minus 0.23. So it means the next step or the step size should be minus 0.23. So we go another step here. This is minus this 0.23. This step is 0.23. Okay. And so the new intercept is 0. We can calculate the new intercept, which is 0.8. So this point here is 0.8. So 0.8 is from here to here, 0.8. Okay. So this is the new intercept value. This value is 0.8. This value is 0.8. This point. Okay. So we can see here the first step we took is much smaller than the second step we took. This is how gradient descent is working. And if we take another step with the new intercept, we can calculate, we will get the result of 0.89 because it's much closer to the optimal value of the intercept. That's why the step is getting smaller. And then we take another step, it will be 0.92. Yeah, and in the end, after 6 steps, we will get the intercept of 0.95. So if you are solving this linear regression problem by least square method, you will also have the same result of 0.95 in this case. So that means the gradient descent has done its job. But however, how we know that the gradient descent should stop, or when we know that it reached the optimal point? So actually, there's no way, but usually we will set some threshold for the step size. When the step size is very small, we just stop the gradient descent. Or there's another method that we can include a limitation of the number of steps. So we can set the amount of steps we want to take when we are doing gradient descent. Yeah. And here's another point I think you may confuse. That is at the very beginning. So I've talked about here that the new intercept is the old intercept minus step size. So why we use minus here instead of plus? Because we are doing gradient descent, right? And when we are calculating the slope here, or the gradient here, the direction is here, is positive. Oh, and then we want the points, the next step taking in the opposite way to decrease the gradient. And that's why we need to use minus here instead of plus, okay? This is why we use minus here. Okay, then let's have a look like, yeah, so let's have a break first. And then let's have a review of the whole procedure of gradient descent. Okay, we'll have 10 minutes break. Thank you. And if you haven't taken the attendance yet, you can take the attendance here.
Mhm.
Okay, so let's come back to the gradient descent. So let's have a review of what we've talked about. So in the gradient descent, after we've chosen the model, the function of the model, which is a linear function here, the first thing we did is to decide to use the sum of squared residues, as the loss function. Okay, so the first thing to do is to decide the loss function. And then we took the derivatives of the loss function, like what we do here, calculate the derivative of loss functions. And then we pick a random value of the intercept, random value for the intercept. And for example, here we set to 0 in our previous example. And then we calculate the gradient. After we calculate the gradient, or we see the slope here, it also means gradient. After we calculate the gradient, we calculate the step size for the next step. So here we multiply this slope by a learning rate. This is a factor with a small value, okay? And then we calculate the new interval based on the new step. The new intercept based on the new step. And the new intercept is equal to the old intercept minus step size. And then we calculate the new intercept and calculate the new derivatives of the new intercept. And then we just iteratively doing this procedure and until we reach a certain steps or a certain small step, depends what we set. So we can either set the number of steps we want, or we set the threshold of the step size, which is close to 0. Yeah, and so here are some mathematical formulations of gradient descent. So yeah, similar with what we talked, we use a linear function. And then we have a loss function. We decide the loss function to try to calculate the parameters in this linear function by gradient descent. And this cost function is also called loss function. Then we do partial derivatives, okay? So because in the previous example, we only have one variable, but usually you will have multiple variables here. So you will have also multiple parameters, thetas here. So you should do partial derivatives of this loss function. And okay, yeah. So when you are doing partial derivative, okay, you are doing derivative on the parameters, okay? You're doing derivatives on parameter. The parameter of the variables, okay? And when you put the value of each data point inside this formula, the x and y will be a constant value, will replaced by constant value. So that's why we are doing derivative on the theta here. And the update rule here is the previous parameter in the, or we say the current parameter in the current step minus a learning rate alpha multiplied by the derivative or the gradient of this loss function. This is the update rule. Okay, so alpha here is the linear rate. It should be a very small factor. I think usually we use like around like 1 multiply 10 to the power of -5, something like this, around this value in machine learning. Yeah, so here is an example when we have two parameters, number of parameters. So this example is just like when we have the function of fx equal to theta 0 plus theta plus theta 1x. Oh, sorry, this is the step of the gradient descent. Okay, when we have two parameters here. So when we have only the number of parameters is 2, then when we're doing gradient descent, the formula for theta 1 is like this. And then the formula for theta 0 is like this. For theta 1 is like this. Okay, so these are the formulas for the gradient descent for this linear function as an example. So n equal to 2 here means we have only 2 parameters inside this linear function. Yeah, and this is a very simple example. Usually we have much more parameters in the machine learning model, but here is just for you to understand how gradient descent work. So we give you the easiest example here. Yeah, and here are some types of different gradient descent. Okay, and I don't think it's very important to know. You just need to know about this. Stochastic gradient descent. So it's like it uses a subset of the training set to do gradient descent every step. Every step it uses a different subset in the data set to do gradient descent. So it means stochastic gradient descent. Stochastic here just means random, okay? They just want to make the name sound more advanced. That's why they put stochastic. Actually, it just means random. And here, batch gradient descent means use all of the training instance in each iteration. Usually, we don't use this one, okay? And we usually use the mini batch gradient descent. So we use a small batch. So a batch here means a subset of the data set. So sometimes we also call it batch, okay? So in machine learning, we have a lot of terminology created by different people. And yeah, a lot of terminology, they have the same meaning, but they created a lot of terminology to make the things sound fancy, okay? So here the batch is just a subset. Okay, and all these kind of gradient descent is just like special cases of gradient descent. Some different types of gradient descent, but all their underlying rule is the same as gradient descent. And actually, when you are doing like neural network or this kind of thing, usually you will only use this add-down. A-D-A-M. Yeah, add-down optimizer. Usually use this one, add-down optimizer. It's also a variant of gradient descent. So it solves some limitation of gradient descent, and now usually we use this one. It could be the optimal optimizer. And I think we are going to talk about it later maybe, but it's not necessary for you to understand it now. Okay, then after we train the machine learning model, we've talked about the generalization problem. Like if you can have a good performance on the new data set that you have never seen. So sometimes, so we have 3 different occasions. The best one is like the good fit or a robust machine learning model that it can generalize very well to the new data. And sometimes there's something called underfitted. So that means your model is too simple. Let's see. Here, you should use like to fit this data. Probably you need to use a quadric function. Okay. Probably you need to use a quadric function to fit the data. But at the beginning, you choose a linear function. You choose a linear function like this to fit data. Then the model is not able to fit all the data. And then it means underfitted. And then if you change the model, or you change the function to a quadric function, then it can maybe feed the data very well. Okay. Of course, actually, this is not a quadric function, but just an example. Okay. I see it might fit better. And what means overfitted means that you give a too complicated model. And then instead of learning the pattern of the data, it just memorize all the data by a very complicated function. So like this. So this means underfitting. So this is overfitting. So it's like you, if you still remember the things we talked about in the first lecture, we talked about memorization and true machine intelligence. So this is like when you're doing overfitting to the data, it just memorize all the data. And then if it give you some more data, let's say it give you some more data point here, okay? So some new data point may be like this, but your machine learning model learned some functions like this, in this way, right? And then when it's doing prediction of the new data point here, the loss will be very big. It is far away from the real data that you have. However, like in this good fit or robust model, if we have some new data here, the model can still fit it well. So this is what means overfitted. Yeah, so you need to carefully choose the model, like the functions and how complicated the model is, and also all the parameters, hyperparameters. You need to tune it carefully to get a very robust model. Okay, and then there is some method called regularization to mitigate overfitting. Okay, and this first regularization method is also called like ringed regression, and it's referred as L2 regularization. Okay, so it means 正则化, and it also sometimes called L2 范数. Okay, so it's have this similar meaning, regularization. Okay, so in this regularization, it's very simple. We just put extra term here, which is the summation of all the parameters in the model. So the theta here is the parameters in the model. Okay, so we have we have in total m parameters here, and we just sum up those parameters. Maybe we sum up n of those parameters, and we have a lambda here. It's a factor. Like decide. This is also called the regularization coefficient. Okay, so it decides how much penalty we give to the model. So actually, this concept is very simple. So the problem of overfitting is usually like you have too many parameters. And so how we mitigate the influence of these parameters? So we want to sum of the parameters being very small. And so that's why we put an extra term here. When this parameter is big, then this term will be very big. So it means the loss function, okay, this is the loss function. It means the value of the result of the loss function will be very big. So it means when theta increase, the loss will increase. Okay, so we put like a penalty of the theta. So that's why when we are doing training, the model will try to make the theta smaller to decrease the loss. And that's why, and when the theta is smaller, then the variables will have smaller impact on the model. And then it will, it can sometimes avoid being overfit. Okay, this is how this regularization work. And also we have another method of regularization called L1 regularization, also called lasso regression. Okay, if you have a comparison between these two regularization method, actually they are very similar. So we also have a lambda here. Sorry, it is blocked. Here's also have a lambda. Okay, and here in the L2 regularization, we are summing up the squared value of the parameters. But in this regularization method, we sum up the absolute value of the parameters. And then the difference between the L1 and L2 regularization is that in L1 regularization, the parameter will be some of the parameter will be 0. Okay. And it's because like the absolute value, the curve is like this, right? So the parameter will tend to go to this point of 0. So you have a lot of term of 0 in your trained model. I mean, in the parameters of a trained model, a lot of parameter will be 0. And so L1 regularization is also doing something like feature selection. Feature selection. Feature selection. Feature selection. Okay. So when the parameters is 0, it means this feature or this variable in the model is not considered. So that's why it's also doing something related to feature selection. Okay, but this, you don't need to deeply understand these points, but just to have some idea of regularization and how it is doing. Sure. And also, when we're talking about parameter, usually we have two kinds of parameter. One is the parameters, another is the hyperparameters. The parameters means the parameter inside the model that you are going to train. And hyperparameters are the parameter that you decide how the training process will be like how many neurons in your neural network, and like what's the batch size you choose, and what's the learning rate you use, and what's the regularization coefficient you use. So these hyperparameters decide how your model is trained and how your model looks like. And the parameters are the parameters that is going to learn during the training. Okay, so hyperparameters are defined by you, and parameters are defined by the model, are learned by the model. Okay, this is a difference between the parameter and hyperparameter. Okay, yeah, so this is the end of this class, and I also want to mention something about the assignments. So yesterday was the deadline of the first assignment, Lab B, right? Let me open the. Yeah, Lab B. Yesterday is the deadline. And for Lab 3, the deadline is 10th of February, okay? So, I mean, for all the lab groups, your deadline is the same, 10th of February, okay? So because I find there's no way to set a separate deadline for different lab groups. So I just put them as the same as suggested by the program leader. And yeah, so for the students who take labs like on Friday, it might be a bit tougher, but yeah, I hope you can achieve it. Okay, yeah, I think that's the end of this class. Thank you very much for your time, and see you next week.